Let's move on to generating the root file system. We're going to use a build system from the Yocto project called Pocky to do this. There are a couple of other build systems out there that you can use to help you build a root file system, like Petalinux or Build Root, but I find that Yocto gives you much more visibility and flexibility in what you can add to your custom root file system. And it's also widely used throughout the embedded system industry, so it's a useful tool to learn. Let's first start with downloading all the dependencies for your system. These dependencies can be found in the Yocto manual, so I'll include a link in the description so you can copy and paste them from the manual instead of typing everything out here. Next, you need to grab the Pocky Git repository from Yocto's website. Just type in Yocto in the search bar, and it should be the first result you get. Scroll down and click the button that says BSPs and Archived Releases. Instead of grabbing the latest branch, we're going to grab the Zeus branch. I tried all of the other branches ahead of Zeus up to the master branch and had issues building the root file system for the Zybo board, so we're just going to stick with the Zeus branch for now. Now we're going to copy this git clone command and paste it into the terminal, and I want to go back up a directory, so I'll cd into Zybo Z7-20, and again, like the other times, I'm going to do a git submodule add command instead of a git clone. Once that's downloaded, you'll want to cd into the directory and source some environment variables for the Pocky build system with this command, similar to what we did with the Xilinx tools. After that command, install the dependencies to run Toaster, which is Yocto's web server for configuring and interacting with the build system. You can do that with the following command. And now we can start the Toaster web server with this command. If everything was successful, the web server should now be running on your local machine at port 8000. To view the web page, open up a web browser and type in localhost:8000. You'll be presented with this introduction page. Now it's possible to do everything via the command line instead of using the Toaster web interface, and using the command line is a very good way to automate things with Pocky. But using this web interface is a bit more intuitive when first introducing someone to this massive build system, so we'll stick to using Toaster for this video. Create a new Toaster project by clicking Create Your First Toaster Project to run Manage Build. Then name the project whatever you want. I'll name mine RobotDog. Change the specific release branch to Zeus, then hit the Create Project button. This is the main homepage for your Yocto project. The first thing you'll want to do is change the machine architecture type to Zybo-Zinc 7 so that everything you build with Pocky will be for that specific architecture. Click on the edit icon, then click View Compatible Machines. Search for Zybo, and you should see the Zybo-Zinc 7 machine. Add the meta Xilinx layer so Pocky can get the Xilinx related elements and scope, then you can click Select Machine. Now, Pocky knows it will be building for the Zybo-Zinc 7 platform. Next thing we'll do is add some environment variables so that Pocky will know that we want things built and configured a certain way. The first environment variable we'll add is a license variable. I'm going to put GPLv3 here, but if you want a different license associated with what you're building, you may want to have a closer look at the documentation for this variable. Also, I've experienced Pocky failing builds if this license variable is not set, so you should at least make sure that you include this variable. The rest of the variables I'm setting here involve the configuration for a runtime package management system so that you can add software packages to your root file system while your system is running. These configurations get used when you're building the package management tool for your root file system like apt, dnf, or yum, so if you don't care about putting a package management system on your OS, you don't need to add these variables. If you do want a package management system, you'll need to change the package feed URI's value to the IP address that will be hosting your software packages. This variable tells the package management tool on your OS where to point to get the software packages. This will usually be on the same computer you have your Pocky build system on, since Pocky is the thing that's generating the software packages for you, but you can host the built software packages somewhere else and then point the IP address to that instead. You can also always change this IP address later on in your OS within the package management config files. I'll go over how to do this as well as implementing the package management system on your Pocky build computer a little later in this video. For now, let's move on to actually making the root file system. It would be a pain if we had to construct all the pieces of a root file system from the ground up. Luckily, Yocto has a bunch of pre-made root file systems you can choose as a baseline to build up from, or to even just use as is if you wanted. To customize one of Yocto's baselines, we'll first need to choose which baseline that we want to start from, and then compile it with the Pocky build system. First go to Image Recipes, and then search for Core Image. We'll be choosing Yocto's Core Image Minimal Dev recipe, which is a bare bones image with just enough stuff in it to bring up the system and allow some basic development work. Pocky is currently going out and collecting all the software packages that it needs and is building it from source, so naturally, this will take a while to build. This took my computer about 30 minutes to run. Here I'm running htop, which shows my CPU utilization on all the cores as the image builds. This image that Pocky's building will contain the root file system, along with a bunch of other potentially useful artifacts to help bring up your embedded system. Some of these artifacts we've already manually built ahead of time, like U-boot and the Linux kernel, but there are some other things like a U-boot environment text file which we'll take advantage of later in this video. But you might be asking yourself, if Yocto already generates the U-boot and Linux kernel for me, then why do I need to go through the trouble of making it manually? Well, from my experience, it's usually less of a headache in the long run to manually grab and make U-boot and the Linux kernel yourself. Since you know exactly where that source code is coming from, there are less chances you'll run into issues when placing it on your embedded system. Or if you do run into an issue, you'll have more visibility into the software components to potentially do something about it. It's probably also worth mentioning that you can make your own image recipes from scratch in Yocto instead of using baselines like what we're doing here, but that requires a lot more in-depth knowledge of Yocto and the Pocky build system, which is far too outside the scope of this video. Once the build is finished, you might notice some warnings. I'll usually get a few warnings here every time I build, but as long as the build completes, the warnings are usually nothing to worry about. For reference, here are what my warnings are. Going back, if we click on the image that we just built, Toaster displays some nice statistics about the build, including a rough summary of your configuration, what tasks were executed, how many recipes and packages were built, and what artifacts were built. There are other performance metrics about the build as well, like the time each task took, the CPU usage for each task, and how much disk space each task took up. There's also a whole bunch of other stats that you can look at about the build as well. Something I find really cool is that you can look at your directory structure right from within Toaster for what your root file system will consist of. For example, you can expand bin and see many of the binary executables that you'll have in your root file system. Now that we built up Yocto's baseline image, we'll make a new custom image from that baseline. Head to the new custom image tab and search for the core image minimal dev image that you just built. Now type in a name for your new custom image you're about to make. I'll call mine Robodog Image Minimal Dev, then click Create Custom Image. Now we can start adding individual software packages on top of the baseline image we built. To find these packages, click on your project name at the top and go to Software Recipes on the side toolbar. I know I'll want to interface with the Zybo board remotely over Ethernet, so one of the things that I want to get is DropBear, which is a lightweight SSH and SCP implementation. I'll build this recipe, and after a few minutes, you'll have a DropBear binary that's compatible with your platform. I'll also probably be running some Python scripts on Robodog, so I'll get Python 3. Same process here, we just search for what we want, then build the recipe. So another thing that I'll want is DNF for my package management tool, so I'll build that one too. Once you're done building everything that you want, go to the Configuration tab and go to Custom Images on the side toolbar. You should see your custom image you named. Click on your image and find all the packages you built. So one of the packages that I built was DropBear, so once you find it, add that package to your root file system. Here you can keep track of how big your file system is getting as you add more software packages to it. Now I also compiled Python 3 and I want to include that, so let's look for Python 3 and add that to your root file system. And for DNF, looks like that's already automatically added. Once you've added all the software packages you wanted to your root file system, go ahead and click Build Robodog Image Minimal Dev. Once that's done building, we can click on our custom image and check out various stats like we did with the baseline image.